Okay, people, in this one, first of all, please excuse the hair. I washed it yesterday and it's Sunday, so this is what we're working with, unfortunately. Alright, today what I want to go through is what we found out last year for moderation to do with the most successful prac reports. They came with these key features that you can see over here, and it's probably no surprise or no secret that the most successful ones had these things. So in the prac reports you need to show evidence of designing something, manipulating some apparatus, so some sort of prac skills. You also need to be able to analyse your results in terms of physics, in terms of the content that we're going through. You need to be able to discuss your findings using appropriate language and terminology, and you also need to come to some sort of appropriate conclusion that's kind of linked to your hypothesis. So we started getting you guys to do this back in year probably 7 or 8, so hopefully by now that's not so much of a surprise. Conclusion is clear. Alright, so there's some sort of clear conclusion. Other things we mentioned in class the other day about when you're quoting specific results in your prac report, we're not, when I say specific results, I don't mean 10.4873 meters per second, because you're going to sound like a little bit of a peanut. What I'm talking about is, let's just do this, quoting to an appropriate number of significant figures. Alright, so if you're quoting me, what do I have, like 3 decimal places, 4 decimal places, if you're quoting me that instead of that, you're assuming that you know more about the experiment than the people who design these things to begin with. So people like Isaac Newton and Einstein later on in the course. Alright, so the experiment that you are currently working through, and this is probably going to be generic for the rest of the year, is going to give you some sort of chance to design or develop your own hypothesis. So when you're developing your own hypothesis in order to construct your own investigation, what you're looking at is the materials that you've got, and you're looking at the relationships that you're investigating between variables, and you're trying to formulate something that will allow you to manipulate one piece of apparatus and produce a result at the other end. So you're effectively looking to, in the circular motion experiment for example, you're looking to change one of the radius, the hanging mass, or the rotating masses. Alright, so what you're doing is manipulating these things and seeing what sort of effect it has on the square of the speed. And then you can use one of these, things to do with the analysis in terms of the content. So in this case here it would be force is mv squared on r, relate that to F equals ma, and you can come up with some sort of relationship between the speed squared and one of these 3 other variables. Alright, so what I'm hoping to do, or what I've been planning to do, is to leave these things open as open as possible so that you can actually do that. So when you're making your hypothesis, what you should be doing is manipulating some apparatus, or saying something along the lines of it is expected that should the radius change, the speed squared will change in proportion because blah 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 blah. It is expected the relationship will be linear because blah 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 blah. Alright, so you need to have your hypothesis, what you think will actually happen, or what you expect, not think, because we're expecting it to happen because there is a relationship. So what you expect to happen, and a decent sort of explanation about why you expect that to happen. So it's no good telling me I expect that the more rubber stoppers there are rotating, the slower the speed squared will be. That's good, that's what we expect to happen, but you also need to explain why that's going to happen. Alright, the why part is the bit that adds depth. Now, point number 2 up here, to do with two variables. So in any sort of science experiment, it's pretty much impossible to change one variable, and if there's, if we're changing, let's say, the radius and the mass, work out what effect that has on the speed squared, because we don't know if it's that one or that one. It's possibly both, it's possibly neither, it's maybe a combination of the two that's actually having an impact on our control or our dependent variable. Okay, so we need only two variables, because then it's a fair test and we can interpret results, and we can interpret these results reasonably fairly. So we can actually draw a conclusion. It's Sunday afternoon. We can actually draw some sort of conclusion. Once again, it's based on the content that we've been discussing, and it's based on the appropriate physics concepts, language, terminology, and it's also related back to your hypothesis. So if you had a hypothesis that included something along the lines of changing the radius and the amount of hanging mass will have a significant or have a linear effect or a constant effect on the speed squared, which one are you actually drawing a conclusion about in your conclusion? How on earth can you know whether it's that one or that one? Alright, so you need to be able to design a hypothesis that can be tested with two variables. Alright, the last couple of points, so conclusion linked to hypothesis of physics, I think I've kind of covered that through here. The clear presentation of data, what we're talking about here is, you've got access to Excel, you've got access to Word, you've got access to a bloody ruler. Use these things, alright? So have tables with the headings in the column headers, and also having the units in there. Okay, so if you start putting, let's say that this was the radius, if I put 20 centimeters in there, Excel doesn't know what the hell cm is. It doesn't know what 20 of them is either. It just thinks that's a word. It's a stupid word, but it doesn't know that. It's a dumb computer. It does know what 20 is. It does know what 0.2 is. Leave the units out of here. Get rid of them out of there. Put them there in brackets. Now Excel can be used to do the calculations for you. Alright, so clear presentation of data makes it a lot easier for you to keep track of what's going on, makes it a lot easier for the moderators to keep track of what's going on, makes it an awful lot easier for me to trawl my way through what you've actually got going on there. Other things to remember, sig figs, because of the experimental accuracy and the accuracy of the equipment we're using. Alright, the very last point, I'll change into a different colour so we don't get too lost in whatever else is going on up here. Discussing specific values. So your data is unique. Oops. Okay, it's unique. It's very unique. It's your data. It's not my data. It's not anyone else's in the class's data, and it's not anyone else in the state's data. You might get data that's actually very similar. You're doing the same bloody experiment, so you'd expect that to happen. But your data is unique. You did the experiment. Okay. So you talk about your your data. It's not someone else's. It's you can use Newton to explain the links between these variables over here. You can most certainly do that, but your data is unique. You need to refer to it. So if you're able to discuss, if you can do that, if you can discuss your data, it shows that you understand what's actually happening. Alright, rather than you manipulate some equipment and some numbers just magically appear. You made them appear. Where did they come from? What do they mean? How do they relate to each other? Alright, so if you're able to discuss specific values from your experiment in context, then you're able to show me that you know what the hell you've done. And you're able to tell me a little bit more about this experiment and uniform circular motion in case of the first one, or what are we doing next? Conservation of momentum, so conservation of momentum or light, etc., etc. Throughout the year, you're able to actually relate what you've done to the content, because you're able to talk about specific data that's unique for you. Okay. The performance standards that have traditionally been kind of poorly done: I1, AE1, AE2. Okay. I1 is to do with your planning. It's you coming up with some sort of experiment based on two variables and also why you've got them in order to do a fair test, be able to draw the conclusions. A1, A2 is the analysis stuff, and it's here. It's where else are we? It's all the way through here, and it's partly, I guess, this table of data, although it's more I3. Okay, these are the performance standards that, as a moderator, I look at first. So if I'm thinking, oh, is it an A? Is it an A minus? Is it an A minus or a B plus? These are the performance standards. These ones, because they are the heart and soul of experimental physics or experimental sciences. Developing some sort of plan and conducting your test, collecting some data, being able to analyse and evaluate or interpret what that data means in context of the physics. Okay, so in context of what we're actually studying. All right. If you've got any questions, come and find me. Refer back to this video as many times as you need to. I've tried to keep it a little bit generic, so that we can keep going back to it. This is probably a good starting point, I guess, but don't get stuck in sitting just with this part. Okay.